Hello, everyone, and welcome to the MRQ Network's 20 Minutes of Science, which are short, popularized scientific presentation in line with the network's research areas. Today's presentation will be in English. However, during the question period that will follow, you will be able to ask your question in French, so you can just write it in the chat and I will translate it. I will do the best I can. And now, please turn off your microphone if it's not still done. And yes, so just for the new people I just met, the presentation will be recorded. It is presently recording. And today our guest is Yira Hurtado. Sorry. Yira is a chemical engineer, graduated from Colombia National University. In 2016, she was awarded a grant by the Colombian government to start working on academic research under the Young Researchers Program umbrella. In 2017, she became a member of the Michael Polanyi Surface Phenomena Research Group. The next year, she obtained a scholarship to carry out her master's studies in chemical engineering at the same university and graduated with a meritorious thesis in 2020. Well done. Her research experience is related to the synthesis, characterization, and utilization of nanoparticles for applications in the oil and gas industry, emphasizing enhanced oil recovery techniques. She is currently pursuing her doctoral studies in chemical engineering at the University of Sherbrooke, and she's a member of the Laboratoire des technologies de la biomasse. This time, her focus is to obtain liquid fuels for biomasse. Her research is under the umbrella of the Ceresis project, a project founded in Europe by the Horizon 2020 called the New Frontiers in Research Fund program in Canada, and the FRQNT, I'll say it like this, in Quebec. Yira, I give you the floor now.
Thank you so much, Christine. Hi, everyone. Thanks so much for attending. Like Christine said, I'm gonna be talking about my research topic. This time, I'm gonna focus on biofuels, and the title that I gave my presentation is From Syngas to Nanofuel, to Biofuels. And this is the outline of the presentation, and we can go ahead and start. So the Ceresis project, like Christine mentioned, is the research project that my research work is under. And the project is funded by 3 organizations and Europe Horizon 2020 call. Here, the New Frontiers in Research Fund and the FRQNT in Quebec. The objective of the project in general is to use energy crops as a soil remediation technique for producing biofuels, and that those biofuels are gonna, they're gonna be using energy crops to soil remediation technique to decontaminate sites that are being used in industrial, agricultural, and military use, both in Europe and in Brazil. And then that biomass is gonna be converted to biofuels to thermochemical processes. The objective is to use those biofuels to replace part of the fossil fuels that are used massively in Europe and Canada, here in Quebec too. The gasification, the biomass is gonna be transformed into biofuels through thermochemical process. One of them is gasification. And gasification is a well-known process in which a carbon source like coal, natural gas, or biomass is transformed into syngas by heating the biomass or the coal or the natural gas into around 7,500 to 900 degrees Celsius with a very limited supply of oxidizing agent. In this case, the gasification part of the process is gonna be done in the Karlsruhe Institute of Technology in Germany. And the source of carbon is gonna be biomass, so the overall footprint of the process is gonna be decreased because of the renewable nature of the carbon source that is being used. The product is gonna be syngas, and syngas is a mixture of hydrocarbon and carbon monoxide, of hydrogen and carbon monoxide, and it can be transformed into methanol, dimethyl ether, ethanol, synthesis, synthetic natural gas, hydrogen, and also into biofuels. And in that case, the process is called Fischer-Tropsch synthesis, and that's the part that I'm gonna be working on. Fischer-Tropsch synthesis can have a different range of products, generally hydrocarbons going from methane to waxes. The nature and the proportion of the products depends on the type of catalyst that is used and the reactor that is used. So depending on that, you can get fibers, you can get fuels, you can get lubricants, and even detergents. This is the overall reaction for the Fischer-Tropsch synthesis, and it's a reaction that is carried out over a solid metallic catalyst. And when it happens, it releases a lot of heat. It is a thermic reaction, so temperature control is one of the key parameters when designing the process. The temperature that is used in this Fischer-Tropsch synthesis is around 150 to 350 degrees Celsius. The lower end of that range actually limits the reaction velocity and also the conversion rate. So in reality, the minimum temperature that is used is around 200. And if you go about 350, what you're gonna do is that you're gonna produce more methane than other types of hydrocarbons. And you can also produce coke, which eventually will deactivate the catalyst. The reactor that is used is pressurized because that increases the conversion rate of the process. And if you go over in pressure, you also be producing coke, so you'll be deactivating the catalyst. So the pressure is also a parameter to keep in mind. The syngas composition actually affects what type of products you get. So for a coal and biomass, you will have a proportion of hydrogen to carbon monoxide of around 0.5 to 1.5, 1.7. And for natural gas, you will get higher proportions, so around 1.8 to 2.5. So that is also a tricky thing to do with the gasification because you want to increase the proportion so you get the type of products that you're interested in this case, biofuels. While the reaction is happening, the Fischer-Tropsch reaction is happening, other side reaction happen. The first one being methanization. And you can actually control how much methane you produce by precisely controlling the temperature of the process. The other reaction that happens is the water gas shift reaction. And in that case, it will always happen because you're producing water with Fischer-Tropsch synthesis. So what you want to do is that you want to switch the equilibrium to the reverse side of the equation, and you can do that by changing some parameters in the reaction. So because there is an interest in producing synthetic fuels, the research has been focusing on finding a catalyst that has high performance and is low cost. The ones that receive most attention are the ones that can produce hydrocarbons that have high molecular weight. So in that case, ruthenium, nickel, cobalt, and iron are the ones that are receiving more attention. So ruthenium is the most active catalyst for Fischer-Tropsch synthesis, but it's expensive. Compared to iron, you will have to spend around 70,000 more money than if you use iron. So in industrial application, it doesn't actually, it's viable to use this metal. For nickel, it's less expensive than ruthenium, but it generally tends to produce more methane than other types of hydrocarbons. So you want to avoid using nickel for this specific application. So that only leaves cobalt and iron, like the viable industrial catalysts that are used in Fischer-Tropsch synthesis. And I will talk about the characteristics of each of them in a minute. But first, I want to mention the types of supports that are used, because cobalt and iron are generally used as precipitated catalysts. That means that they're a powder, so they need a support. The supports that are used generally, mesoporous material like alumina, silice, titanium, zeolites, MOF, or nanotubes. What is important to control in this case is that the interactions between the metal and the support are not as severe as the interactions between the metal and the syngas, because then you will be reducing the activity of the catalyst and stuff. I said that I will go back to talking about cobalt and iron, and that because I want to talk about them specifically in terms of the conditions of the process. So for iron, you will get a very wide range of temperature, pressures, and Syngas compositions that you can use. But this catalyst is actually less active than cobalt. So what you're gaining in a range of operation, you're losing an activity of the catalyst. However, this catalyst is the least expensive. So compared with cobalt, it's 230 times less expensive than cobalt. So you're losing yield, but you're gaining in the cost of the process, right? And the operation parameters. Cobalt has a lower range of operation, so in temperature and Syngas composition, but it has more activity, around 4 times more than iron. So in this case, you will have to do a task of thinking of my operation parameters, what type of products I want to gain, in the cost of the process itself. One thing that also has to be kept in mind when choosing the reactor, the catalyst, is that you will have to think about the composition of your syngas. So for biomass, the one that is produced from biomass, it generally doesn't get to 2% in the ratio. So you will have to add a conditioning unit. So you will have to add more things to the overall process. So it's a toss-up, right? Right now I have a toss-up between cobalt and iron, and I'll have to determine what parameter is more important. I also have to choose what type of reactor to use. I said that depending on the reactor, I can get a different product. So if I use a fluid, there are only 3 colors that I can use. And if I use a fluid as the reactor, the products that I will be getting will be low molecular weight hydrocarbons. So gases, gasoline, and some olefins. And in that case, the only catalyst that I can use is iron, because I will have to be in the high temperature range of the process. But the interest of Ceresis is not actually that type of product. We are thinking in high molecular weight hydrocarbons, so diesel type fuels, waxes that can be then transformed into fuels. So that leaves me with 2 choices for reactor, a fluid size bed reactor and a slurry reactor. And I'm gonna speak about the benefits and the limitations of both of them. So for a slurry reactor, I can get a very good isothermal operation because it's easier to control the temperature when the medium is liquid and is in constant contact with another liquid that I'll be using as the refrigerant in this case. I also can have a very high conversion rate because I can use catalysts that have a smaller size. So that increases mass transfer, and mass transfer increases the yield of the process. Because the particles of the catalyst are suspended in a slurry, I will have less pressure drop in the system. So my compression cost for the overall process is gonna be less. And it's easier to replace the catalyst in the reactor because it actually leaves the reactor with the product. But then again, that is a disadvantage. That can become a disadvantage because then I will have to add a unit, a separation unit that is gonna try to separate wax that is very, very viscous from very small catalyst. Right now, there is only one technique that is used for separating this type of products, and it's proprietary information. And what it uses is centrifugation and electromagnetism. So I will have to add a different unit with this type of characteristics to the process to be able to separate my product. And this type of catalyst also has difficulty in the scaling up process because it's very hard to predict the fluid dynamic behavior of the three main components. So my catalyst that is a solid, my product that is a slurry, a wax, a very viscous slurry, and the gas that I'm injecting, the syngas that I'm injecting. So predicting that means that I have to do a simulation process, and simulation is not cheap. It's a very expensive process. So scaling up the Fischer-Tropsch process when I'm using a slurry reactor is expensive. The other type of reactor that I can use is a multitubular fixed bed reactor. And the benefits of using this type of reactor is that the temperature range that I can use is a little bit wider. Also, I can separate the catalyst from the wax very easily because it actually trickles down the bed and is collected at the end of the reactor. And in the case of contamination for the catalyst, I can actually contain it in the top part of the reactor and save the rest of the bed from contamination. It's also very easy to scale up because what happened in one tube is what is happening in each tube. So with one tube, I can predict what is gonna happen in each step of the process. So I can go from lab to pilot very easily and from pilot to industrial scale also easily. The limitations of this type of reactor though are that the heat transfer is complicated because I have to ensure the gap between the catalyst and the two walls is small, so I can rapidly remove the heat of the reaction. But if it's too small, then the pressure drop increases. So my compression cost will also be increased. And what I can do to try to control the pressure drop is to use particles. They are bigger, so my catalyst will have a larger size, and that reduces the conversion rate. So the yield of the process is gonna be reduced as well. And maintaining this type of reactor is complicated because each time that the reactor deactivates, I have to replace it periodically, and that is a cost and a labor-intensive process. So I have to shut down the reactor, and then I have to empty it, clean it, then I have to fill it again, and then start the process again, and that is time-consuming. So although the process has been thoroughly investigated for the production of syngas, and there are commercial catalysts that are being used, the process overall has the argument for research are the fact that I have to do a toss-up between what type of catalyst I'm gonna use and what type of reactor I'm gonna use. So if I go with a cold reactor, I will have to add a conditioning unit to the reactor to be able to meet the Syngas composition that I require. And also the activation temperature for cobalt is higher than the process itself, so I have to activate the catalyst outside of the reactor, and that also increases the cost. But then if I choose an iron catalyst, I'd be losing I'll be losing mass transfer efficiency, and that means that the yield of the process is gonna be less. So again, I have to do a toss-up. And when it comes to the reactor, if I choose a isothermal operation, then I'd be losing efficiency in the transfer, in the heat transfer, and in the mass transfer. So I have to think of that. Or if I choose a slurry reactor, then I will have to think of a way to separate my product efficiently, and the escalation process will be cost intensive. So this type of problem makes the production of synthetic fuels very, very expensive. So right now there's only 4 plants that are using this type of process, and they use fossil fuel as the source of syngas. So for me, it's important to figure out a way of manufacturing syngas, biofuels, using a source that is biogenic, so like biomass, and that it doesn't have social high costs. And what that will mean is that combustion engines could become neutral in their carbon emissions if I can find a way to reduce the cost of the operation. So the objective of my research is to improve the manufacturing process of synthetic fuels using Fischer-Tropsch synthesis. And in this case, what I'm gonna do is that I'm gonna use an structured catalyst. Structured catalysts are ceramic or metallic extrusions. They are pre-shaped in the form of a single continuous structure, and it has a stable geometry. So in that case, it can be a monolith or an open cell form. And this type of reactors are actually being used in environmental catalysis with very good results. So they are used in car exhausts to reduce the production of greenhouse gases. And it's also used in power stations to reduce the production of nitrogen oxides. Those applications have shown that if I use this type of catalyst, I can reduce the pressure drop in the system, because there is a high void fraction that is not gonna make it so difficult for the syngas to get to the active sites of the catalyst. I can also improve the heat transfer efficiency for the same reason, because I have a defined structure. I can actually make the size of my 2 walls smaller, and that's gonna mean that I can rapidly remove heat from the reaction. And the last thing that this type of structure provides is that the geometry makes it very possible to have a very good mass transfer. So my yield is gonna increase because the conversion rate is gonna increase. So with this type of reactor, what I hope to accomplish is that I can use it to improve the temperature control of the process, and also reduce the size of the reactors that are used. And that way they can be implemented in a syngas processing plant that doesn't have the production capacity of a coal plant or a natural gas plant. So I can actually lead to a more efficient way to produce synthetic fuels if I use this type of reactor. So what I've done so far is that I designed the experimental setup for my process. In this case, I'm gonna use a tubular fixed bed reactor, and I'm gonna use a structural catalyst. In this case, I'm gonna use iron-based structural catalyst. Right now, I'm constructing the reactor, and this picture shows what I have done with the catalyst. So I have produced a structure that is metallic and it's open cell. And you can see that the rugosity of the catalyst is actually high. So that means that mass transfer can be efficient and the conversion rate of the process can increase. I mentioned that my project is funded by these 3 institutions. And if you want to know more about the process, you can go ahead and visit our page. And at Sherbrooke University, I work with the Biomass Technology Laboratory. This is our team. And we are working on biomass valorization. We are trying to upgrade from biomass to fuels, that means producing hydrogen, pellets, synthetic fuel, syngas, you name it. We're trying to do valorization of biomass in every stage. These are our partners. And if on any of those topics that I mentioned is of any interest to you, please don't hesitate to reach out. Thank you so much.
Thank you very much, Yira. I just stopped the sharing. What you do seems really complicated to me. All the graph you, but the picture of the reactors, like, 2 slides ago, I was like, what, you did it? It is now the question period. So I invite you to open your microphone to ask your question, and also you can write it in the chat, and in French or in English. I will translate it in French. I don't know if, but I read that the syngas was toxic, corrosive, and acidic. Maybe it depends of the source, but I was wondering if it is what I read, if it is, and if there's any health or environment risk associated with the storage and the process of the syngas.
Yes, actually carbon monoxide is kind of corrosive. So we actually have to, when designing the process, we actually have to take into account the severity of the gases that we're using. And what we do is that we do signalization, we put alarms. So if there is a leak, we can actually contain it. And the university has helped in every step of the process. But yeah, those two components are actually toxic, and hydrogen is also not only toxic but it can explode. So we are trying to apply all the measurements that we can. So we have signalization, we have the alarms, we try to have the security for the process very, very tight. So there is like minimum risk when operating the reactor.
Thank you, Yira. Is there any other? Oh, I think I have a question in the chat from Mayara Alil. Just one question. How do you do the synthesis of the catalyst at the lab?
Well, right now what I'm using is that I'm producing a slurry, a metallic slurry, and that metallic slurry then I use to coat a polyethylene foam. Once the slurry covers the foam, I put it to dry, and then after drying, it goes to a sintering process. So first I had to burn the polyethylene foam. So the template that I use, I burn it. And then after it's burned, I have to sinter the catalyst so it retains the structure. But yeah, it's like temple replication, the technical name for it.
Okay, thanks. Any question from people in the room? I suppose you're limited by the equipment and the reactors that are available at the laboratory. Maybe I think you have a great equipment. I don't know what to say.
Actually, that has been kind of a problem, an issue that we have. So right now I'm building the reactor, but we've been waiting for the parts for a long time because this process is new for our lab. So each part of the reactor had to be like purchased and is assembled. And this week I received the final part of the setup, which is the oven. And so I'm very, very happy that I can like start to do tests with the catalyst and stuff.
Okay, that impressed me that you are building that.
Yes, we're building it.
Do you have other questions? Avez-vous d'autres questions? Vous pouvez les poser en français si vous voulez, puis je vais les traduire en anglais.